Welcome. We will discuss optimality issues in 2 to the power k factorial design. So, before going to the optimality issues, I will discuss with reference to 2 to the power 2 design that the regression surface as well as how the regression coefficients are estimated. You have already seen this one, but I want to repeat it. So, you see this page, and I am 100% sure that all those terms written here is known to you. The first one is talking about the geometric representation of 2 to the power 2 design. Here we have two factors a and b. When you use the same thing in regression, we denote them by x 1 and x 2. And x 1 has two labels, x 2 also has two labels. The labels are denoted by -1 and +1 as high and low respectively. And when you conduct experiment keeping both the factors at low level or -1 level, the total observations what you obtained with reference to the y, the response variable denoted by within bracket 1, when only at a at high level it will be represented by a, only b or x 2 at high level it will be represented by b, and when both the factors will be at high level it will be represented by y. Y will be total of y will be represented by a b. Okay. Now, the same thing when we use the geometric sign, that algebraic signs. So, the geometric view analogous representation in algebraic sign is this. What here we have 4 treatment combinations, 1 a, b and a b, and x 1 or a is having the values -1 +1 -1 +1, x 2 -1 -1 +1 +1, and if you multiply both you will get x 1 x 2, that is a b factor interaction a b, or x 1 and x 2, this will be +1 -1 -1 +1. Okay. And the corresponding y total exactly the treatment combination what the way we are basically following. We are writing in this fashion. You may write in other way, but this is what is the practice. Then you see left hand side here, I have given you the regression equation with that is basically first order regression equation with interactions for this 2 to the power 2 factorial design. So, here y equal to beta 0, beta 1 x 1, beta 2 x 2, beta 1 2 x 1 and x 2. So, beta 0 is the intercept term, beta 1 beta 2 are the main effect, beta 1 2 is the interaction effect and error. So, the same can be written in matrix form y equal to x beta plus epsilon, where y is the response values at different experimental runs, x is the design matrix, beta is the regression coefficient to be estimated, epsilon is the vector representing the error terms. Okay. So, then come to this side. Here what happened in this particular equation with what are the different terms, like x. First, here there are 4 independent observations in the sense I am saying independent treatment settings, and either the average or the total at each independent treatment settings is considered here. We are considering here total, sometimes average also can be used. Now, the first column is actually contains all the 4 ones, this is for beta 0. The second, third and fourth column with reference to beta 1, beta 2 and beta 1, beta 2, that is from estimation point of view. Other way I can write that this first column is beta 0, here 1 x 0 is multiplied, which taken all the time value 1, and second, third, fourth column with respect to x 1, x 2 and x 1, x 2. So, this is known as design matrix. This is the response vector, this is the error vector, and there is another vector called beta, which is beta 0, beta 1, beta 2 and beta 1 2. This part is known to you. Now, when we ask you that you estimate the parameters, what you will do? You will find out SSE, which is epsilon I square sum of I equal to 1 to here number of observations, that may be, let it be n. Okay. And then what we do? This will be nothing but y I minus beta 0 minus beta I 1 x 1 minus beta I 2 x 2 minus beta I 1 2 x 1 x 2 this square, and obviously I equal to 1 to n number of observations. Okay. Then you will find out del SSE by del beta 0 put 0, del SSE by del beta 1 put 0, or similarly del SSE by del beta 2 put 0, del SSE by del beta 1 2 put 0, and then get you how many equation you will get. For how many parameters? 1 2 3 4 equation you will get. Solving these 4 equations, you will be getting all the estimates. Okay. So, this is what we will be discussing. Now, content is basically the optimality issues with, and when we are talking about optimality issues, it is related to the to the variance optimality, variance, because you are what you are doing, you are estimating beta. So, what will be the your best estimate, that which is basically having minimum beta variance of beta estimate. So, using this equation y equal to x beta plus epsilon, suppose that you can use it for prediction purpose, y will be x beta cap. Now, you want to minimize the variance of predicted portion. So, similarly, there are different estimation issues here, and for every such cases. So, depending on the situation, your design may help you to optimize the situations like variance, minimize the variance for the beta estimate, minimize the prediction error. This is what is known as optimality issues in 2 to the power k factorial design. As such, this is true for any regression model, and this is true for all kind of regression design. Only the mathematics portion will change little bit depending on the design and the data available. Okay. So, these issues we will be discussing here, and we are basically taking the information from this book, that Montgomery book, chapter 6. So, the explanation I have given you, that if you find out the SSE, and then basically if you just go for SSE by beta 0, beta 1, all those things, you will actually estimate the beta values. This part we have seen earlier, I have shown you earlier also. So, now here what happened, in addition to that, we are actually what I am giving you, because as x 1 and x 2 takes only minus or plus 1 values. So, if you put this into this all those minus 1 and plus 1 and this, then you are basically getting this matrix. What is the matrix? What is the matrix? Basically, matrix actually I am giving you here, and all those things, this matrix, that beta 1, beta 0, beta 2, all those things, this is the application. So, we have 4 y values, 1, a, b and a b, and x 1 column, x 1 column is minus 1 plus 1 plus 1, see minus 1 plus 1 minus 1 plus 1, x 2 minus 1 plus 1 plus 1, and this one minus 1 plus 1 minus 1 plus 1, and this. So, if you just write down separately, what you will get? 1 is beta 0 minus beta 1 minus beta 2 plus beta 1 2 plus epsilon 1. Okay. And then the estimation point of view, this is what is the formula, least square, ordinary least square formula, x transpose x inverse x transpose y. So, if your data x is this one, then x transpose will be this, and then when you multiply these two, you will get a very interesting matrix here. You see the diagonal elements are 4, off diagonal elements are 0. Getting me? So, here you come back to this, you have 1, 2, 3, 4 independent, basically distinct observations here. Means at each experimental setting you may get many observations, but you are taking total or average of this, and then you are making them as distinct observations. So, there are 4 because of it is 2 to the power 2 design. If it is 2 to the power 3, it will be 8, 2 to the power 4, it will be 16, like this. So, these 4 things are now, if you want to include that, no, each observations also will be the replications will be there, then it will be 4n 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 4n, it will be there like this. Now, if you multiplied x transpose into y, another interesting one, you are getting this. This also I have explained earlier. So, now what happened? You are basically getting this, if you think that that means the second, third and fourth, these are nothing but the contrast for that is A, B and AB effects. Okay. So, left hand side, that means now beta cap is multiplying these two will give you what? So, if you take the inverse of this will become, diagonal element will become 1 by 4 and off diagonal element will remain 0, and then your calculation will be like this. So, all the contrast, this will be divided by 4. So, the x transpose x matrix is diagonal because 2 to the power 2 design is orthogonal. This is the key things here we wanted to show you. So, because of orthogonal design, so you are getting off diagonal elements 0, there is no covariance dependency between them. And here, when the least square estimates of the model regression curve exactly equal to 1/2 of usual effect estimates, that also we have seen earlier. If you estimate the effect, you will you will write down contrast by 2 to the power k minus 1 into n, contrast by 2 to the power k minus 1 into n, that sense you do. So, 2 to the power, now if as we have taken total or average, this part will not come. So, it will be by 2 to the power k minus 1, then contrast by 2 to the power 2 minus 1. So, it will be contrast by 2, that will be the effect of A, B like this. But here is the regression coefficient, we have shown you that beta j is regression coefficient and effect is A j, then this is the relationship earlier we have shown you. Okay. So, with reference to this x transpose x beta and the prediction part y cap, then we will explain now the optimality issues. First of all, what will be the estimate of variance of beta? If you recall the regression lectures, there we have shown you that variance of beta cap is sigma square x transpose x inverse. Okay. Actually, the estimated, if you know sigma square, you would straight away write down sigma square. Suppose I write sigma square this. Now, that is because you have beta 0, beta 1 like this. But if I want to know the, this is other way we have written as covariance. Now, if I write variance of beta j cap, then this is sigma j square the jth element of jth diagonal element of x transpose x inverse. So, x transpose x inverse for 2 to the power 2 design is 1 by 4, 1 by 4, 1 by 4, 1 by 4 and other part is of diagonals are 0. So, that means everything divided by 1 by 4. So, actually what happened then? So, variance of any beta component any beta cap will be sigma square by 4. Okay. Now, and this is what is the minimum variance. This is what is the minimum variance. Okay. Now, let us read out the points here. The minimum possible variance of any model regression coefficient in a 2 to the power k design is sigma square divided by 2 to the power k into n. Now, a design that minimizes variance of beta cap is known as d optimal design. So, this is it is a mathematical issue that d optimal design, but from the practical practice point of view, but from our application point of view. So, a d optimal design is one which minimizes the variance of the estimated parameters here. Now, the d terminology is used here because it maximizes the determinant of x transpose x. The d is coming from the determinant part. So, that is why it is known as d optimal design. And 2 to the power k design, the way we have explained, the actually that is what the 2 to the power 2 k design also. The 2 to the power k design is a d optimal design and it for first order model and first order model with interactions. So, essentially what we have done then, we have explained from optimality point of view that variance of beta, this should be minimized, and it is done in 2 to the power k design using the least square estimates in the manner that it optimizes the determinant of this or maximizes this determinant of this, and collectively this of design is known as d optimal design. So, what do I mean? That d optimal design is one which minimizes the variance of beta cap, and 2 to the power k design is d optimal design. 2 to the power k design with first order with interaction also, it is d optimal design. Okay. So, this is the first. Second, we will see another variance. Suppose when we say y cap is x beta cap, and many a times what happened, we will be interested to know the variance of predicted value. Okay. So, that means variance of predicted value that may be variance of y, suppose x 1 and x 2. Here we are writing y cap x 1 and x 2, because only 2 to the power 2 design we have taken for explanation purpose. So, then what will happen? What will happen to this? This will be beta 0 cap plus beta 1 x 1, beta 1 cap x 1, beta 2 cap x 2, beta 1 2 cap x 1 and x 2. This is the predicted part. So, that means you are interested to know the variance of beta 0 cap plus variance of this plus beta 2 cap x 2 plus beta 1 2 cap x 1 and x 2. Now, x 1 x 2 all those things are fixed values, because you have seen the design matrix. So, can it not be written that this is now again what I mean to say that this beta 1 beta 0 this orthogonal design. So, that you have seen the covariance part of beta b 0 is 0. So, because of independence we can write that this is beta variance of beta 0 cap, then x 1 square variance of beta 1 cap plus x 2 square variance of beta 2 cap plus x1 square x2 square variance of beta 1 to cap. So, what is beta v variance of beta 0 cap? That is sigma square by 4, we have seen earlier. So, then x1 square into sigma square by 4, x2 square into sigma square by 4 plus x1 square x2 square into sigma square by 4. So, it is sigma square by 4 into 1 plus x1 square plus x2 square plus x1 square x2 square. Okay. So, this is variance of predicted response. This is known as variance of predicted response. Suppose all if x1 x2 0 0, what will happen? So, this value will be, suppose then variance of y cap given x1 equal to 0, x2 equal to 0, this value is sigma square by 4. If variance of y cap x1 equal to 1, x2 equal to 0, so this will be what will happen? This one will be sigma square by 2, or other way this is equal to variance of y cap x1 equal to 0 and x2 equal to 1. If we put variance y cap x1 equal to 1 and x2 equal to 1, what will happen? This one sigma square by 4 into 1 plus 1 plus 1 plus 1. So, this will become sigma square. So, this is what is the maximum variance that can occur in the response when you predict, because when all x1 and x2 both are at the high level 1, x1 1 x2 1. So, that means that the corner points basically, as the everything is the square term, whether x1 1 or plus 1 or minus 1, those corner points that maximum variance occur. Okay. So, what we require then? We require a design that will minimizes the maximum of predicted variance. So, you want a design that minimize the maximum of predicted maximum variance, maximum of variance of predicted value. So, minimize the maximum variance for the predicted response will occur at the corner points, and you want a design that minimize this one. This design is known as G optimal design. Okay. And to the power k design, factorial design is G optimal with first order and model, first order model and with interaction model, and model with first order model with interaction are G optimal. Okay. So, this is the second issue, second optimality issue here. Now, you read out this point, third here the last but one point. The smallest possible value of the maximum prediction variance over the design space is p sigma square by n, where p is the number of model parameters and n is the number of runs in the design. This is what is the smallest possible value of this maximum prediction variance. 2 to the power k designs are G optimal designs for fitting the first order model and first order model with interactions. Suppose you have lot of points. So, you want to see that what will be the predicted variance for at a lot of points. You are not basically predicting at one point, you have lot of several points. So, that means what will happen, you will find out different kind of variance at different predicted variance at different points. So, under such situation what happen, you will basically find out the average prediction variance. So, we are talking about average prediction. So, this average prediction variance is denoted by, you just first find out the total area. Here we have the, what is the design space, x 1 minus 1 2 plus 1 and x 2 minus 1 2 plus 1. So, within this design space, what is my variance of this one, that predicted one, x 1 x 2. So, you integrate this dx 1 and dx 2. This is basically total you are getting. Now, once you divide it by the area 1 by A, so then you are getting the average prediction variance. This is the formula. Okay. So, now let us think a 2 to the power 2 factorial design case. What is this? So, this is minus 1, sorry, let me write it then, minus 1 plus 1. What is this length then? Minus 1 to plus 1, this is 2. Similarly, minus 1 plus 1, what is the length? This is 2. So, what is the area? 2 into 2, 4. So, I will write this then 1 by A, here minus 1 to plus 1 and then minus 1 to plus 1, and then what is this value? You have already seen what is the predicted variance of this. I think variance of this, you see, we have written variance of this equal to sigma square by 4 into this. So, you write down this one as sigma square by 4 and this is 1 by 4, I am writing A equal to 4, 1 by 4, sigma square by 4 into 1 plus x 1 square plus x 2 square plus x 1 square into x 2 square d x 1 and d x 2. So, first you do it with reference to d x 1, then put the values and d x 2 put the values, then the resultant value will be 4 sigma square by 9. So, in 2 to the power 2 design, average prediction variance is 4 sigma square by 9. Now, what you want? You want also this to be minimized. The minimization of average prediction variance, when you have say a lot of points to in the design pairs, you are predicting the values at a lot of in the design space, lot of values. So, this is known as I optimal design. I optimal design. Okay. So, so these are the few things you learned, that your design is when you develop regression surface. So, that time how you use regression equation, that is that you have learned earlier. Today we have repeated this thing. Then we say that when you are estimating some of the parameters, the variance of those parameters to be minimum, and that is in mathematics known as d optimal design. So, we have seen that 2 to the power k design is d optimal for the first order and first order model with interactions, and then we have shown you that g optimality. So, g optimal design is one which minimizes the maximum prediction variance, and we have seen that our 2 to the power k design is g optimal, and finally, I optimal design. And here in the case of 2 to the power k design, the I optimal value is 4 sigma square by 8, and this is I optimal also. So, this is little bit advanced topic for that optimality issue. That optimality issue we will be dealing further in detail in response surface, when we discuss response surface methodology. That time this optimality will again come, and we will discuss to some extent there also. Okay. Thank you very much. Hope that you have enjoyed this class also.